Okay, guys, so can you hear me?
Yes,
Okay.
sir.
Okay.
Yes.
Okay. Okay. So first of all, the announcement about exam. So there is a class test. So class test. This is on September 7th. September 7th. Okay. And this is Tuesday. During the class time, so it is from 12 to 1 p.m. And the syllabus is first two modules of the syllabus of this course. So I have shared the syllabus, detailed syllabus of this course. And the first module is probability. So which includes this axiomatic definition of probability, conditional probability, total probability, Bayes theorem, independence of events, and so on. So this module, probability, the first module in the syllabus, is a part of this exam. So this is called the axiomatic definition of probability, and whatever we discuss, basically conditional probability, and okay, total probability. We talked about total probability theorem, our formula, total probability, and Bayes theorem, independence of events. So these are basically whatever we have discussed regarding the first few lectures. So that's a part of module 1, and this is a part of the syllabus of this exam. And the second module is also part of the syllabus. So the name of the module is random variables. So, okay, we have started talking about random variables, and we said, okay, we spoke about discrete random variable and continuous random variable, and then okay, probability density function or probability mass function, and then there are a few things which we'll be discussing today and tomorrow, and we'll see. I think we'll be able to complete the syllabus by tomorrow. So this PDF probability density function, CDF, the cumulative distribution function, then expectation, or in general, I would say moments. Moments are central moments about the origin, and then moment generating function, a median, quantiles. We'll see. We'll discuss all this, quantiles, and Chebyshev's formula, or Chebyshev's inequality. So these are the topics which are included in the syllabus. So you should prepare for the exam. Okay, and if there is an issue regarding during the exam, you just immediately can drop an email to me. If there is any issue related to accessing the exam page, or I think it will be conducted in Moodle. If there is any issue accessing Moodle, then also you should immediately write an email to me. I'll contact the concerned person here, and he should get back to you immediately. Okay, so this is the syllabus for the first class test on September 7th, first week of September, on Tuesday during the class time.
Sir, could you please scroll up once?
Yeah, this is available actually. I just wrote it down although, but this is available. So I uploaded a document named Detailed Syllabus 2021-2022 Autumn. So the first PDF which I uploaded or shared in Microsoft Teams. So everything is available there. So the first module is probability, and the second module random variables. These are the parts of the syllabus. So these are anyway available to you. So you can access it in Microsoft Teams. Okay, so it is available. Okay, so now we'll proceed because we have to complete the syllabus. So yeah, so what did we discuss last day? Is basically we talked about what is random variable, and we denoted it by X. capital X, and we said, okay, whenever we'll be discussing any concept, topic, whatever it is, so there is an underlying probability space, meaning there is a sample space, there is a sigma algebra of event or sigma field, and there is a notion of probability. So this is the probability space, and a random variable introduced as a function. So this is nothing but an association of sample points with real numbers. So we are representing sample points as real numbers. So this is just a representation of the sample points, so that so I introduce it like a mathematization of the random experiment or the sample points. Okay, so that we can deal with it. We can use our machinery of calculus or anything else like which we have studied in mathematics or in basic courses like linear algebra. I mean, basically math 1, math 2. Okay, we can use this machinery in order to analyze probabilities of events. Okay, so basically we have a sample space here. There are sample points, and it could be finite or infinite. If it is countable set, that means it is finite or countable infinite sample points, then we call it discrete sample space. Otherwise, we call it continuous sample space. And then this is the real line assume. Then so this is an association. So of real lines, real numbers with the sample points. And this is what is called X. This is the random variable. So random variable is not a variable. Random variable is not random. It is just a function from S to R. And here R means the set of all real numbers. And then we talked about, okay, what is called a discrete random variable. Discrete random variable. This is a random variable whose range set, or we call the space of the random variable. So which is nothing but, since this is a function, it has a range set. If the range set is a countable set, so the range set meaning all those numbers, let's say R, real numbers, such that R is equal to X of S. So these are all R. Let's say here, all numbers are here. So I'm writing it as a variable. This is true for some S is in S. So here some S is here. This is my sample space. So this is the range set. We denoted it as Rx, the range set of X. If this set is countable, then we said, okay, this is called the discrete random variable. And then we introduce the concept of what is called the PMF, the probability mass function or probability density function. What we said is, okay, this is a new function we are defining now, F. So this is called a PDF, corresponding to the capital X random variable, the random variable, or the discrete random variable. So it is PDF or PMF. So in general, we'll call it PDF, but for discrete, it is called PDF, PMF, and for continuous random variable, it is called PDF. We'll talk about continuous random variable today. So this is a function, you can say from range X, okay, to 0, 1. How it is defined, we said f of X is equal to probability of X equal to X, small x. Now how it is explained, this is an event. This is an event. So the event is now described in terms of a random variable. So here you have some number, let's say X here. Then you are looking for the pre-image of this X, like for all those sample points here, which are mapped to the small x. Okay, so this is the event. So this is the probability of the event, which is described as follows. So this is all such sample points such that X is equal to X, small x. So this is the event, corresponding event. So we looked at an example how to construct this function given the random variable. Today we'll see one more example, simple example. Let us start.
Capital X is a random variable.
Yeah, capital X is the random variable here. Yeah, this is the function.
Oh, okay.
Yeah. So now let us consider an example. Let us assume that we have a fair coin. Okay, suppose a fair coin. Fair, as I always said, whenever we say in this course that something is there is something which is random. Okay, we always assume that the possible outcomes are equiprobable. That means they are equally likely, so they have the same probability. So we can say the fair coin, meaning it is so it is unbiased. So it is probability is, let's say, whatever the probabilities are. Like here, coin means head and tail, so it is probably half and half. So suppose a fair coin is tossed. It's tossed, let's say, 3 times. Okay, and let's say the random variable, let's say x, okay, is defined as follows. Is defined as the number of heads. The number of heads in these 3 tosses. Okay, and then the question is, find what is the PDF. Okay, find the PDF or the PMF. Find the PMF corresponding to capital X. Okay, a very simple problem. So first of all, we need to find out what is the sample space. So sample space could be what? This could be tail, head, all possible. There are 8 possible outcomes: TTT, TTH, okay, THT, HTT, THH, HTH, HHT, and HHH. Okay, this is the sample space. So okay, now so I can assume that this is the sample space. There are some points. Yes.
One outcome you wrote the twice, first and second, TTH, TTH in sample space.
Okay. So let me say TTT. Okay, sorry. So then we said, okay, here I can assume that this real line has a vertical line. Then correspond to each of these are like TTT. Then this value will be number of heads is 0 here. This will be mapped to 0. Then let's say for TTH or THT or HTT. So these 3 points, this will go to 1. This will go to 1, 1, and so on. Okay. So depending on the number of heads. So as we discussed before, random variable is nothing but it is measuring something, okay, about the sample point. It could be height, weight of anybody, something, some number. It is associated with the sample point. Here it is number of heads. You can consider something else as well. Then we can see that this Rx is nothing but the possible range is nothing but 0, 1, 2, 3. I mean, among all these numbers, real numbers here. So this is, let's say, the real line. But the range set of this function is nothing but 0, 1, 2, 3. These are the only points in the range set. Then we defined, okay, what is called F0. If you want to PDF or PMF, and this is probability that x equal to 0. So x equal to 0 means all such sample points which will take the value 0. So here this will be nothing but a set TTT. So its probability will be 1 by 8 because all are equally likely. So there are only 1 point here in the event, so it is 1 by 8. Similarly, we can have F1, which is probability of x equal to 1. And so then you will see there are 3 points here, so it will be 3 by 8. Then we'll have F2, which is probability of x equal to 2, which will be 3 by 8 again. And then we'll have F3. So this will be equal to probability of x equal to 3 equal to 1 by 8. So this is simple and nice. Now the question is, if I ask you, okay, write this as a function. What is f(x)? So you have to give a functional representation of this entire process, of this entire function. So that means I have to define a function, let's say f of x here. So f is a function from this Rx to 0, 1, okay, such that when the value of x is 0, then it will give me the value 1 by 8. When it is 1, small x equal to 1, then it should give me the value 3 by 8. When the small x equal to 2, then it should also give me 3 by 8. And when small x equal to 3, then it is again 1 by 8. And then what is the functional representation of this? And if there are maybe multiple functions which you can find out that this is possible. One way to write it is like this. There's a reason why I'm writing it, but you can say that this is also a representation of this function, half to the power 3 minus x, when x equal to 0, 1, 2, 3. By the way, so this is called the PDF or the PMF. So this is a construction of this PDF as a function. Okay, these are the values. So I want a function. So basically, what is happening here is, if you want to draw this, plot this. Okay, so here this x is okay, like okay, here it is 0, 1. Okay, here let's say 2, let's say 3. Okay, let's say 4, and so on. So I want this fx. So this is my x, okay, and this is fx. So these are some value. Let's say it is 1 by 8, and then this is 3 by 8, and then this is 3 by 8. Okay. Oh, this is 1 by 8, then this is 3 by 8, this is 3 by 8, and then again it is 1 by 8. So something like this. So this is these are the functional values. Okay. This is the function here. This is my fx. Okay. Now, so in other books, I mean, in many books, they treat this function as a function, need not be from Rx, but it is from entire real line. So it is, you can say minus infinity to 0, 1, or you may assume like it is from R to 0, 1, same thing, okay? And then what is happening, then you have to add one more line here, okay? So you have to say like this values is this, and then you have to again say 0 when otherwise for other values of x. Okay, sometimes you have to write like this. Okay, so it is their way of defining the function, but it is very easy when you just define it for Rx. So it is only valid for those points which are in the range set. Okay, this is another way of doing the same thing. In some books, you'll find like, okay, they define probability mass function like this, like from entire real line, and then when it is the point in the range set of the random variable, then it has this representation, some representation, and otherwise it is 0. Okay. Now the question is then, ultimately everything boils down to this f. So why not I consider a function like this, and then I go back to the corresponding random variable, and hence I go back to explaining probability of the events corresponding to the random variable. Then the question is, in fact, this is what we'll do in the entire. So this is how you can use the machinery of calculus, okay, in order to analyze the MX. Now see, everything boils down to this particular function. So then the question here is, for what kind of function, what are the properties? The question is, what are the properties? So if I just start with any arbitrary function, will it represent a PDF or a PMF corresponding to a discrete random variable? That is the question. Okay, can any function be treated as a PDF or PMF for some random variable? That's the question. So now you see, as I said before, we'll gradually forget everything: sample points, sigma field, sigma algebra, probability function, everything we'll forget. We'll only focus on this part. That suppose I am supplied with such a function f, and then what can I say about the probability of the corresponding event of the associated random variable? Now, how the random variable is associated here? Once you have f, once you have the small f, then I know that small f is defined as this. So there is an association with the random variable, which is probability of capital X equal to small x. And this capital X is the random variable associated with this PDF, associated with this PM for the function here. So then the question is, what are the properties or the characteristic properties of a function, let's say any function f, from some R to 0, 1, I mean, some particular function, some subset of R or R itself, the entire R, such that it can be treated. Okay, it can be treated, or it can be some subset or some Rx. You can assume whatever the subset here you are considering, that can be considered as a range. Okay, such that it can be treated, or you can take the entire R. So it can be treated as a PDF or PMF or PDF. Okay, for some random variable. So how the random variable is defined? Defined by that small f of x is equal to probability of capital X equal to small x for some random variable, okay, x. That's the question. And to answer this question, we have a theorem, but let me just write it as an idea, okay, write it as a definition, but you can prove this also. Okay, so suppose.
Sir, can you explain this question once more? It was not clear.
Okay, so there are three things here. One is this sample space to a real line. So these are all the random. This is random variable. Let's say, I mean, not from one point, but they are from different points. Okay. So this is a function. Now, once we have this function, then we define this PMF, which we talked about last day. PMF is from 0 to 1. And how it is associated? So this capital X is again from the range space of here. Range space of this is a function. Range space to here. This is small f. So we started with S. Then we have some X, which is from S to R. And then we define f, which is from range days to 0, 1. Now, if I know the sample space, if I know the random variable, then I can find out the PDF, which I explained in this example also. So when I'm supplied with a random experiment, I know the sample space. Suppose I define a random variable, so the random variable is given to me. Okay, then I can find the PMF or the PDF. But here I'm asking the reverse question, meaning I know only a function. Suppose this is given to me somehow I can find it out. Okay, and the question is, this must explain some random variable, or can it be associated with some random variable or not? That is the question. So if I begin it from here, so I am supplied with some function, okay, some value, some function, okay, suppose it is discrete, so I'm talking about a discrete random variable. So suppose this values are given to me, okay, this could be countable infinite or finite, okay, for all this x's, this value, this function is given to me. Then the question is, okay, can it be treated as a PDF for some random variable or not? That is the question here. Okay, and if it can be, then my question will be, okay, how to consider how to find, let's say, the probability of the events corresponding to the random experiment, which is explained by the random variable. So I'm reversing the entire process because I want to play with this function because I know how to play with real valued functions. Okay, that's the idea. So what are the properties of, so if I give you any function like this, okay, any function like here in the diagram, so can I treat it as a PDF or PMF for some random variable? Okay, that's the question. So suppose a function f is given to me, okay, for some values like this is given to me for some subset of R or inter R itself is given. Then the question is, does it represent oh, I already have written the question, this one. Now to answer this question, okay, I can just write it as a theorem, or I can just write it as an idea, because it can also be proved, so I can treat it as a theorem. So let x be a random variable with range set, let's say Rx. Okay, this is not known to me, and or maybe this is known to me if I go in the right arrow direction from left to right. So x is let's say x be a random variable, range set x, and let's say with range set x, and let's say PDF or PMF fx. Okay, then you can observe one thing, which is fx is always non-negative. How? Because fx is then defined as probability of x equal to small x. So since this is a probability, so it is of course non-negative. And second thing would be, you can also prove that the sum of these values should add up to 1. Which will add up to 1. So these are the properties which you can observe, okay, the properties of a PMF. So then the idea is, okay, so can any function be treated as a PMF of something? I'll say yes, provided it satisfies these two properties. So if the function is given to me and it satisfies these two properties, then I'll say, okay, it represents a PDF for some random variable. For example, let me consider an example. Let's say my function is like this. Let's say fx is equal to k, and k is a constant, 2x minus 1. K I don't know, okay, this one. And let's say here it is given like x could be up to, let's say 1 to up to 12, x is here. So that means this is the range set of the corresponding samples random variable capital X. The question is, does it represent a random the PMF corresponding to the random variable x, capital X, whose range set is up to 1 to 12? Okay, or for what values of the, or for what values of this k? If it is not, then the question is, for what values of this constant k will it represent a random variable? Now I can check, will it represent a PMF? Now I can check whether this is non-negative or not. For example, I can put the values of x equal to 1. So for example, take x equal to 3. Then I see that 2 times 3 is 6 minus 1, which is minus 5. If I take k to be positive, then it is not non-negative. So this function cannot be a PMF for k to be positive, okay, or for all k to be positive, because for x equal to 3, this is not a non-negative function. Okay, so first of all, I need to check whether it is a non-negative or not, or also I can check whether the sum of this to be equal to 1 or not. Suppose it is the function, suppose it represents a PMF, then I have to check whether, suppose this set is Rx for some x. So whether this is equal to 1 or not. And if I do that, then what I'm checking, 1 should be equal to sum over k 2x minus 1 for all x's in Rx. So it should give me this one is equal to sum equal to k equal to 1 to 12 and k 2x minus 1. If I do it, so then this will be, okay, k, not k, but x. So k then 2 times sum over x equal to 1 to 12 minus 12. So this will be k times 2 times 12 into 13 by 2 minus 12. So it will be 144k. So here meaning k is equal to 1 by this. So if k is equal to 1 by 144, then only it will satisfy this condition. Now I will check putting the value k here, k to be equal to 1 upon 144, and check whether it is non-negative or not. And if it is non-negative, then I will say, okay, for all values of k, this is not a PMF, but when k is equal to this 1 upon 144, then it is a PMF. So that means given any function here, I can check using this definition, these two conditions, whether it is representing a PMF or not. Now we'll introduce another concept which is called which also like is useful for calculating certain other events. Okay, so probability of certain other events. So we said, okay, if x is here, x equal to x, capital X equal to small x, this we discussed. Okay, what are all these events? We also discussed when we write this x x less than b or less equal to b. This also we discussed. This is also an event which is set of all sample points such that the values of these are lying between a to b for any interval a to b, so s for some x. So this is the corresponding. This we already know. So this is so now here we define what is called the cumulative distribution function, or just the distribution function. So it is cumulative distribution function. So associated with this random variable capital X. So this is a function now with fx is equal to. So I am not every time writing what is the domain of the function because it is clear from the context. Capital X less equal to small x. So if here is again, we can assume that it is from R to 0, 1. Or you can say it is from minus infinity to infinity to 0, 1. Okay. So if I know the random variable here, I know this event, then probability of this event is nothing but capital F equal to small x. Okay, so I can just take x here, this is, and then I can plot what fx is if I know everything about the random variable. Then I can find the event, I can find the corresponding probability, and I can do that. Okay, and what is this event? So this is nothing but probability of all. So that probability of the event which contains all sample points such that x value of this is less equal to small x. Okay, so this is the event. This is the event, and this is the probability of that. This is times fx. And if I treat this as a function, so again it is a new function. Okay, now cumulative means I am here consider. So for the PMF, I saw that we defined it like x equal to x, capital X equal to small x here. Okay, if it is x here, so it is exactly the probability here when it is the PDF or the PMF. Now, capital F is what? This is the probability of all those events which are here as well. So they can take the value anywhere up to x. So this is minus infinity extended. For any value here, they can take any. So here was my sample space. Okay, here is my sample space, and here is my random variable. So here is my real line. Okay, I pick any x here. So these are assigned some values here. Okay, some assigned some values here, and so on. So this is my x. So if I pick x here, okay, there could be some value which is going beyond x. So this is x here, let's say. So this is the probability of all the sample points here. Okay, so this is, let's say, all this set of sample points. This is the event which are taking values which is less than the small x, the probability of that, and it is called the cumulative distribution function. So basically, you can just observe. This can again be proved, but let me call it a result or idea, which is like if x is a random variable with range space or with space or the range space Rx, then you can say this fx is nothing but sum over ft t less equal to x, and this is what will happen. So you'll have, for example, here, suppose this is my small fx, then I know for different values of x, okay, I have different probabilities here. Okay, let's say I have this. Okay, I have different for this and different values of x, I have different probabilities here. Let's say I have here also some value. Okay, and then here, whatever it is. So sum of them has to be equal to 1. Sum over all these values should be equal to 1. And they are all non-negative, so they are all these picks. Now, if I pick any x here, okay, so what is the capital Fx? That means it is sum over all these values, because the thing is all these values. Why? Because the thing is that when I am plotting this Fx, some f capital Fx, and this is the real line R. So then if I pick x, then this value fx, this value is nothing but sum over all these values, okay, or t, and t less equal to x, because this is how it is defined. So probability of this, okay, this is how it is defined. So I can say, okay, this is also true. So the thing is, given a random variable, okay, I can find its PDF and I can find its CDF. So PDF and CDF can be found when we know the random variable. So we know how the random variable is defined, then I can calculate the corresponding probabilities of capital X equal to small x and capital X less equal to small x. So I can just compute the PDF. From the PDF, I can compute the CDF. CDF is the cumulative density function or distribution function. So can be found when you know the random variable. Okay. In fact, it is enough. In fact, if I know the PDF, then I can compute the CDF. Then I can compute or find, okay, the CDF, the cumulative distribution function. How? Using this formula of x equal to this. I'll just take the sum over it, and that's how can I get it. Okay. Okay. Now the question is, since this is again a function, okay, this is again a function, you can plot it. Then again the question will be, okay, what are the properties of this function? Okay. So what are the properties of CDF? I'll not prove it, but you can just check that these properties are true. Properties of cumulative distribution function, which are like, first of all, f of minus infinity should be equal to 0. Can anyone tell me why is that? Because no value.
Because there is no value before minus.
Yeah. So these are all the x, okay, and it is saying x to be equal to or approaching to minus infinity. Okay, so that means there is no value, let's say, which is bigger than minus infinity, which or maybe less than minus infinity, which the random variable x is assigned. So this will be the null set basically. So it is 0. Similarly, you can check that f of infinity should be equal to 1, and you can also check that f is an increasing function, or fx is an increasing function. Why it is increasing? Can anybody tell me? Increasing function, meaning if x is less than y, then fx less equal to Fy for all real xy. And why is that? Because it is the sum. Because of the sum. So if you take x here and let's say y here, so then for x you already have added all those values. And when you take y, you have to add these two values along with these values. Then only you'll get capital Fy. So if x is larger than this y is larger than small y is larger than small x, then capital F of y, okay, should be bigger than capital F of small x, okay, because we are just adding up the terms. Okay, this way adding this up will give you this, and adding everything up here, okay, will give you this. So Fy is always bigger or equal to this value Fx when y is bigger than x. Okay, this is obvious. So this is a monotonically increasing function. Then the question will be, okay, I can find CDF from PDF. Can I do the reverse? If the CDF somehow I know, the cumulative distribution function, can I find its PDF? And this is also possible. If you just watch the, if you just visualize this, okay, then you can find it. Let's say this is my real axis. These are the values x1, x2, x3. Let's say x3, let's say x4. Let's say my range space consists of these values x1, x2, x3, x4, and so on. Okay. Now, when you take fx, okay, capital Fx, that's CDF, then there is a corresponding value attached to it. This one. Okay. Then if you take, let's say x2, there is some value here which is attached to it. Okay. Some value you can assume fx2. Let's say because it is increasing, so I'm drawing it like this. It is an increasing function. So I have these values. x4, let's say I have these values. Because it is monotonically increasing, so I'm drawing it like this. So this is my fx1. This is my fx2. This is my fx3. And this is my, let's say, fx4. These are the values. Now the question is, can I find small f of xi's? And what is small f of x1? What is small f of x2? What is small f of x3?
Sir, if we will minimize means that from f of x2 minus f of x1, then we can find f of x2.
Yes, exactly. So if this is the first point, then this value should be equal to f of x1, right? Because there is no other point here. So when you write this, so f of x1, let's say, what is it? This is probability of x less equal to x1, right? Now, there is nothing beyond. So let's say this range set is ordered, meaning x1, the way I had drawn it, x2 less than x3, less than x4, and so on. And there is no value beyond x1. x1 is the least possible value the random variable can take. Then this value is nothing but probability of x equal to x1. Because there is no other value the random variable assumes. So it is exactly the same. With the least one, it is the least one. Then when you increase, then this will be f of x2 minus f of x1, then f of x3 minus f of x2, okay, and so on. You'll get f of xn is equal to f of xn minus f of xn minus 1. So in the exam, for example, if the CDF is given to you and you are asked to find what is PDF, then you can find it out. So why this is true? It follows from this diagram itself. Okay, check the diagram, and then you can find out what is happening here. So this will be just 0. Then anyway, so you can just find it out. Okay, then there will be this one, this value. This will be f of x1. Okay, because for other values it is not taking any value. These are all anyway. So you can find it out. So when you take this sum, when you take this, for example, this x2. Okay, so all these values will add up to 0. There is only one option, which is x1, for which it is taking some value, because the range space is like this. Okay, so when the capital F, the cumulative distribution function, is given to you, so you can always do that. Now, let me tell you one thing. question here is, suppose I start with a random variable, okay? Then I can find it, so from the random variable, I can find its PDF or PMF for the discrete case, or PDF. And from the PDF, I can find the CDF, the cumulative distribution function. Okay, and I also said how to get the reverse. So if I know the PDF and then the corresponding function, then I'll check whether it represents some random variable, and then I can talk about the probability of the events corresponding to the random variable because it is defined by this fx. Then here is capital Fx. And the question is, this process is unique. Like for x, I have corresponding fx. Okay, but for different CDF, okay, or for the same CDF, there can be different random variables. It can explain different random variables. Okay, I mean, this has nothing to do with exam, or you should know this, but I think this is a basic fact which you should think about it, and you will find some nice things about this idea. So what I'm saying here is, for one PDF, one CDF, let's say, can explain or can represent different random variables. If you're confused with this one, then just don't read it, okay? That's fine. So let me just give you an example, then you'll see. Suppose I consider this sample space, which is just head and tail. Let us say x1 of h, this is my random variable, which is 0, x1 of, let's say, tail, which is equal to 1, and another random variable, let's say, x2 of h, which is equal to 1, and let's say x2 of t, which is equal, let's say, 0. And then you calculate its PDF, its CDF, then you will see that they have the same CDF, 0 if x is less than 0, half if 0 is equal to x less than 1, and 1 if x is bigger than equal to 1. So they have the same CDF, although the corresponding random variables are different. That means what is happening here is, suppose you are supplied with a CDF, okay, then it may represent some random variable, but that random variable is not unique. It may explain some other random variable, because random variable is nothing to do only except association of these numbers. So here I have assigned as 0 for head and 1 for tail. Here I assign 1 for head and 0 for tail. So basically I'm doing the same thing, only the representation is different. That means how do you define random variable? It doesn't matter. You always end up with getting the same CDF. If the different random variables represent the similar pattern, that means for the two different random sample points here, you consider two different real numbers to represent them. Okay, so that's the idea here. So CDF is so important. So it can explain the different random variables, however, whatever way you have defined. But if the different random variables, they have the same pattern, they are defined in a similar way. Okay, then the data analysis, what you are doing, it is independent of which random variable is talking about. It will give you the facts about the data. Okay, whatever random variable you consider, doesn't matter if they have the same properties. Okay, so if you consider head as 0, tail at 1, and I consider head as 1, tail as 0, doesn't matter. It gives me the same CDF. Okay. Now, okay, I am doing literally fast today because I finished the syllabus for the class test. But if you have any doubt, you can always ask me. Okay. Okay, the next is we'll consider continuous random variable. Okay, continuous random variable. Okay, and we said, okay, when did I say that it is a discrete random variable? We said if the range set of the random variable, so x here, capital X here, this is the random variable. So association of numbers with the sample points. Now I'll say x is continuous. Okay, discrete when if the range set, okay, if Rx is countable, then we say that it is discrete. Okay, so just remember the picture. This is S, and this is R. This is 0, and you are associating numbers with the sample point. This is X. Okay, this is X. Now we are talking about range set of this function. Okay, so then I'll say this X is continuous if Rx, the space or the range set, is either an interval or unions or a union of intervals. Now here I am again the mathematicians here again are doing a cheating little bit of. So here they don't say that the ring set is not countable. Okay, they only consider all those uncountable sets which are either interval or union of intervals. Why? Because this will give me, or this will facilitate us to compute the probabilities. That's why. Okay, that's the idea. So here it should be either interval anyway is uncountable. Okay, union of interval of course uncountable. So interval means what? This is my real line. I consider some a to b. Let's say a equal to 3, b equal to 13. Okay, doesn't matter. So set of all real numbers here. Okay, so if that is the range set, then I'll consider this as a continuous domain. Okay, for example, say the possible range set is like, okay, some height from some particular number to some, let's say from 5 feet to 6 feet, some kind of a thing. Okay, so this is my range set. Okay, it can take all these possible values. Okay. Okay, so then I'll define the PDF. Okay. Okay. So here there is an interesting thing. Although I say that this is this one, okay, but I have to associate with a PDF. This random variable associated with a PDF. Now here you see, this I explained also before. If I just say fx, this is my PDF, which I defined as this, x equal to small x, then I'll be in trouble. Because for countable or for finite case, okay, when this range set is finite, I have a notion of sum, that sum of fx is equal to 1 when x is a range set. But if I take that this is a range set, if I want to take the sum and this range set become an interval, if it becomes an interval, it is an uncountable sum. So I cannot number, because for uncountable set, what happens is I do not have a notion of first number, second number, third number. Okay, why? Because if I ask you what's the immediate next real number to 3, we don't know. Okay, so we cannot have an ordering of the real numbers because we do not know the immediate next real number. So even we do not know whether it is there or not, because we cannot find it out, what is the immediate next real number to 3, we cannot find it out. So this doesn't make any sense. But somehow I need to define a PDF. So this way we cannot succeed. So I'll define it in a different way. Okay, so this was not my exact definition, but I'll consider this as a definition. So in the definition itself, with the continuous random variable, I will associate a function which I'll call later the PDF. Okay, a random variable x is said to be continuous, okay, or continuous random variable if there exists a continuous function. Now see, continuous function. This continuous function is the notion of calculus continuous function. This notion is not calculus notion of continuous function. Okay, this is a continuous random variable, but I'm not saying the random variable as a function it is continuous. I'm talking about its range set is continuous, meaning range set is either an interval or it is union of intervals. So this continuity here is different from our standard notion of continuous function, although the random variable is a function. So continuous random variable does not mean the random variable as a function it is continuous. I did not say that. I said random variable is continuous when you have this kind of a thing. But when I am properly defining it, formally defining it, I'm associating this random variable with a function which is continuous function. So if there exists a continuous function f from the entire real line to 0 infinity, such that for every set of real numbers a, so a is basically a subset of R, any subset of R, probability that x belongs to a should be a fx dx. So now I'm using integration because this function, existence of this function is a continuous function. I can talk about integration. And that is why this said, so if a is a discrete, I do not know how to integrate it. It will just be the sum. Okay, but if A is an interval, it is in an interval, then also I can talk about integration. But if it is not interval, not discrete, then I am in a shoe. Okay, how to define it or not? But anyway, I'm saying that for all real numbers, all subsets of R, this is the probability. So this is an event which I already know because the sample space is given to me. And X belongs to A means what is that event? Set of all the sample points such that X of S is in A. And A is what? A is a subset of R. Let's say A is suppose some points, some points, an interval, whatever it is. This is just A. So A is a subset of the entire real line. Let's say this is 0, this is infinity, this is negative infinity. So A is here. So X, okay, if it X of S, capital F of X, if this is inside this set A, then I define this as the even a probability of this event is computed as this integration. So I'm associating with a function in order to define my continuous random variable. So random variable is continuous if there exists a continuous function such that this, okay, such that probability of these events can be explained in terms of integration corresponding to this function as an integer. Now, what is this f? This f is then very special, and this f is actually called the probability density function of the continuous random variable x. So here my definition again, the function f, okay, in the above definition, that means through which you can consider probability of an event associated with the random variable capital X in the above definition is called the probability density function of a continuous random variable X. Now see the trick here. Okay, for discrete, what we did, we had the sample space. We defined this X, the random variable, and then we talked about a function, okay, from 0, 1, or we can just say this one, this is X and this is Fx, and all this X, okay, corresponds to an event, okay, and this X will represent probability of X equal to X, this event, and then Fx, let's say here, so this value, this is then probability of X equal to square. But this is the approach we did not consider for continuous random variable. For continuous random variable, we start with this function. So suppose there is a function f, and this function explains, this function gives me this value. So suppose fx is known, which is continuous, and then given any a, subset of a, this value gives me probability of this event. Then I will say x is a continuous random variable, and not only that, this f is said to be the PDF of that random variable. Okay, and of course, then you will see. So this is a property, or this is a fact. This is an idea. You can prove it that for PDF means here now I'm considering for continuous random variable. Earlier I had sum over all these values will give me sum over all these values should give me 1. Here my integration over minus infinity over all the entire domain should be equal to 1. So this is fx, and of course fx has to be non-negative because the way I have defined here, you see, this is non-negative here. Okay, this is non-negative, and this integration will give me the value 1. Okay, so for example, yes.
Yeah, any real life example of this type of distribution, like continuous distribution?
Yeah, I am giving. So here, no, I can give you. See, the thing is, there is a so I will learn examples. I first explain. Okay, in the example, I first explain. Okay, suppose I have an experiment. Then I define a random variable. Then I define its PMF. I calculate its PMF. But here the situation is completely different. Suppose I start with some random variable which can take values inside the interval, okay, or union of intervals, and then I'm asking, what is the small f here? Does there exist at all a small f here? Okay, and I do not know. I am in the dark. I do not know how to find a small f for which that particular random variable can be explained. Okay, so that particular random variable can be explained like this. How to find this f of x? I cannot do that because there is no way to find it out, and there are many options. Okay, I do not know anything how to construct this function. Okay, because there are many options means there are infinitely many functions. I don't know which function will give me a possible way to satisfy this. Okay, so I do not know. So for that, what we will do is we'll start with this small fx, and then we go back to saying that it represents, if it satisfies this property, okay, this property, and it is non-negative, then we will say it represents some random variable, some continuous random variable, and that's it. And the question is, can any function represent a PDF for some continuous random variable? I would say no, it has to satisfy this. Okay. Now the question is, okay, can I give a particular example of a continuous random variable? So basically now everything boils down to calculus here. Okay. I only have to consider functions like this, functions like f of x or f from r to 0, 1, which satisfies this property, and then I have to analyze the corresponding random variable or probability of events corresponding to that random variable. Okay, whose PDF is this given function. Okay, this is how it boils down to. Now, so the question is, can I have a practical example of a continuous random variable? Yes, I can have. When for example, okay, so in practice, in the real world, I can never have such an example where I have a sample point which is uncountable because I do not have nothing to store it. For example, I do not know how to store it because I do not know all the values even, right? So if I say, okay, take the collection of people whose height is between 5 to 6, and I want all the people should take all the values here in the interval. Well, it is not possible because I even do not know the values between 5 to 6 because I do not know the immediate next number to 5. So in real life, this is never going to occur, uncountable. But whenever your number of sample points is high, is large, then I can approximate it using an interval. We'll study this, okay? When we'll talk about Poisson process and so on. There we'll see. Time, for example, time is always continuous, so I have to deal somehow with the continuous thing. Okay, it can be any point, so I can consider this interval time as a completely a. So let's say, so for example, how many customers can come during the time, let's say 5 a.m. or let's say 5 p.m. to 6 p.m. So here somehow, so how many meaning? If I say, then that will be discrete point. Okay, but if we consider the time, that is a continuous thing. The time that is varying with a continuous thing. So somehow I have to deal with continuity, like the continuous domain. And another thing is, whenever the sample points, number of samples are very high, so this is very, very large. It is finite, but it is large. So there are billions of sample points, let's say. Okay, then I cannot just treat this. I cannot just define a random variable for each of this individual point. I can do the analysis. I cannot do that. What can I do possibly? Suppose these sample points, they are real numbers, then I can take the entire domain what that belongs to. Then that is itself a random variable. Those values will give me entirely in this domain. That from the least values to the maximum values, they're lying in between this, from least to the largest one. And then I can consider the entire interval because it comes so many points here. Okay, I possibly can treat it as a continuous thing. So when it boils down to, in fact, you will see machine learning, data analysis, any field of engineering where you have to deal with noise, for example, any phenomena in circuit theory, okay, any phenomena regarding control, okay, control theory, everywhere the noise is assumed to be a continuous random variable which has a particular distribution function. Okay, because noise can be of so many different types, so it can take so many values. It is better to consider it as lying in an interval. Okay, then any value it can take, but in reality it will never take all possible values. But you can approximate it using an interval, and that means it can take all possible values. Okay, inside, which are lying inside that interval. So in reality, what is happening is I'll never get a random variable which will take, I cannot see that, okay? But I can fill it by approximating a large set into a continuous subset of the real line, okay? Suppose I consider all humans in this world. And now if I measure their heights, okay, then maybe it is from 3 feet at the majority of them to, let's say, 6 feet. Now, there are so many sample points. If I'm very, very precise, it could be 3.001, 3.002, 3.1, 3.5, 3.5, 3.57, 3.51, and so on. This could be total variation. And then possibly I would say, okay, this is my range space, the entire interval. So I am approximating it using this interval. And then I am talking about the probability of the events which can be defined by this corresponding random variable for which this is the possible range. Okay, so in reality, it's never going to occur, but mathematically, when you model, you have to do it using this continuous interval or union of continuous interval. It could be from 3 to 6, or from, let's say, 6 to 7, okay, or from, let's say, 2 to 3, whatever it is. So union of intervals or just intervals. Okay. Yeah. So let us see an example. Let us see. Okay. Okay. The way we created an example here. Let us say here this example. Let us say fx equal to c by 1 plus x minus some theta. I'm writing this constant theta because it has a meaning. It is a standard PDF of some standard random variable. Okay. So here my function is defined as this. Okay. So depending on x and depending on c, it can have certain values. So it is never non-negative for some values of c, because this is always non-negative. This value could be positive or negative. So I want to find out, suppose this is the function, then for what value of c, for what values of c, f is a PDF. How do we answer this? The answer is I have to check. Okay. First of all, c has to be bigger or equal to 0. That I know. But for all c bigger or equal to, is it a PDF? The answer may be not. What I have to check is whether 1 is equal to minus infinity to infinity fx dx or not. So if I perform this integration, so this will be minus infinity to infinity c by 1 plus x minus theta whole square dx. And I can assume that this to be equal to x minus theta equal to some value. Minus infinity to infinity c by, let's say, some 1 plus z squared dz, which is equal to, let's say, c tan inverse z, then minus infinity to infinity, which is like c times tan inverse, let's say, infinity. When I'm saying infinity, I'm not doing the inter process. It is some number which goes to infinity in the sense of limit. I'm just writing it down. Tan inverse minus infinity, and then c is equal to, let's say, my tan is inside the interval pi by 2 to pi by 2. So it is pi by 2 plus pi by 2. So this is c pi. So that means the value of c should be equal to 1 by pi. So for this value, c equal to this function is a PDF of some random variable. Okay. So here now, random variables will be described in terms of their PDF. Okay. I'll not first define the random variable and then find a PDF. I'll not do that. Okay. Because my sample space is too large. It is infinite. Okay. In fact, it is uncountable. So I cannot even do that using that procedure. Okay. Because I cannot even calculate what are the values my random variable is associating with the possible sample points. So I always start with the PDF. Okay. For example, here, this is a PDF. The question for which value of c, it will be a PDF. C is equal to 1 by pi. So I have this function now. Is 1 by pi 1 plus x minus theta. Theta is a constant, any constant. So minus infinity less than x less than theta. In fact, this random variable, whose PDF of this is called Cauchy random variable. I picked that example. You will see a lot of specific distributions Okay, a lot of particular distributions which we'll be discussing maybe next week. But here I'm starting with an example because you'll get a flavor that probability is nothing but calculus.
Sir.
All the thing is, yes.
Sir, if the 1 plus x minus theta equal to 0, then what will happen, sir? So it may be 0, sir, at some particular value of x.
Oh, no. It will never, because this is whole square. So this value is non-negative. If it is 0,
Oh,
this...
sorry, sir. Sorry.
Okay. So yeah. So this is not whole square. Here, whole square is here. Okay. So this is called Cauchy random variable. And then we'll say this x, we'll use this kind of a symbol, CAEO, let's say, and the parameter here is theta. For any value of theta is a parameter. And then we'll say that x is Cauchy random variable, and the fx, okay, is called the Cauchy distribution function. This density function fx is the Cauchy distribution function. In fact, you'll see that in this entire course, probability is nothing but calculus in disguise. Okay. Only thing is that here the functions are only of very specific type, and this function, okay, this kind of functions, they represent something which happens in reality, and they are explained as random experiments. That's it, nothing else. Okay, you only have to perform some integrations, this and that, but like calculus course, any function, people can give you any function, and you can talk about its derivative, its integration, and so on. But here everything is meaningful. Here, if you perform derivative of some particular function, they will see it will explain something with attached to reality, linked to reality, connected to reality. It is explaining some kind of an experiment. So all the concepts here, yeah.
One more question, sir. Sir, for the quasi probability, this will not applicable. Means, sir, when the negative event will cancel the positive event, then we cannot find the PDF.
Quasi, what is that? Cauchy or quasi? What did you say?
No, sir. I mean quasi probability.
Quasi probability means
yes,
you are
sir.
not talking about this probability.
No, sir. Just quasi probability means negative probability, sir.
Okay. Yeah. I talked about. I mentioned that thing only in one lecture, but let us forget about it. In this course, we will not talk about those kind of situations. Okay. Here we are doing the naive thing. Naive means which are very, very classical and standard. Okay. So we'll not talk about that. Anyway, so now we can define what is called a cumulative distribution function, or just a distribution function corresponding to a continuous random variable. Okay. So it's cumulative distribution function. Okay, what is that? So suppose we have a random variable, then random variable, continuous random variable, that means it is described by its density function. That's the only way to do it. So let fx be the PDF which is given to me of a continuous random variable x. Sorry guys, I'll not be able to take a break today, or maybe after some time, because I have to finish it. Then the cumulative CDF, this is also CDF fx of x is defined as follows. So I have to define this fx, and this is very simple now because everything here is now in terms of integration. So it's minus infinity to x ft dt. Earlier I had just summation, which is referred by integration, but it has the same meaning. But I'll not talk about it because I do not know what the random variable is, how it is. I don't care, because I know the PDF. I'm satisfied with that, and I don't know how PDF is linked to CDF, because I know for the discrete random variable I have this picture in mind that if I have this individual, but here it will not be individual because it's a complete interval. Okay, then if these are the small f, then I have to take the sum. Okay, sum x is here, then all this t, okay, which are less equal to x, and I have to take the sum over all this. But here I do not have this individual outcomes. I have the entire region here. So I have this PDF. So this was for discrete. This was the picture for discrete. So if you want to find out this fx, then I have to sum it up. Okay, but here this is a little different. Here this f is itself a continuous function. So it is not a discrete function, like it is not defined for all these different discrete values of discrete real numbers. It is defined for an interval. Let's say it is from A to B. Okay, this is my interval fx. Then if I take some x, then I have to just take the area under this, and this area will give me f of x. Because area, because it is an integration. So even if if this is my integration, so basically when I take minus infinity to x, here these values are all 0 for this small fx. So I only have to bother about this because when it is positive. Okay, so I just take the area under this, and this is my cumulative distribution function. Okay, so for example, if you can just if you know Python, C programming, any language, okay, you just plot this Cauchy distribution. Okay, a Cauchy distribution for some particular value of theta. So basically, you have to plot this function considering some value of theta to be equal to half, 1, whatever. Okay, that's why I said it is Cauchy theta. So you will see that you will get some kind of a curve, let's say this, okay, and then you take any value of x, okay, then the area under this is nothing but fx. Okay, so fx is the unit function, cumulative CDF, the cumulative distribution function. Then the question is again, suppose I know the cumulative distribution, I know how to find cumulative CDF from the PDF. Okay, then the question is, how do you calculate PDF from CDF? Okay, so here it is performed by integration. That this CDF is found from PDF using integration. Then the question is, how do you find PDF, the small f, from the capital F, from the cumulative distribution function? And the obvious answer is performing calculating the derivative. Okay, which I'll not prove, but you can find the proof and you can justify yourself thinking about it, how to get PDF from CDF. Earlier we took the differences, here I have to take the derivative. So if fx is CDF of a continuous random variable x, the PDF fx of x is the derivative of fx, that is TD. So derivative here is meaningful. When you come, particularly when you take derivative of a function which is a CDF, then you get the new function which is the PDF. So derivative of cumulative density function or distribution function for continuous random variable, okay, then you can have the PDF, the derivative of CDF. So this is remarkable. Okay, so the CDF is defined using integration from PDF. Then here now I'm finding the PDF from the CDF, then I have to take the integration derivative. And then the question will be here, okay, is it at all a differentiable function that I can take the derivative? Here I assume that it is integrable because I assume that it is continuous on an interval. Okay, it is possible to be integrable. Then the question is here, it is differentiable. Okay, I'll say, okay, keep all the questions in your mind, not for this course, for the time being, or we'll not discuss about it. You may just try to read about these things. But here we'll assume that the CDF function is differentiable and we can define that. Okay, for example, okay, what is the PDF? What is the CDF? What is the cumulative distribution? Or just people will say distribution function. Okay, what is the CDF of Cauchy theta? Okay, that means I have to find out this fx. I have to find out this. So minus infinity to x fx dx. So I have to perform a derivative again here, which is minus infinity to x 1 by pi and 1 plus t minus theta. Okay, I cannot write x here. Write some other variable. T minus theta whole square and then dt. And you'll see what you can do. Okay, in fact, this will be 1 by pi tan inverse x minus theta plus half. This is how we'll get the CDF of this. Okay. Now the question is again, what can you compute from the CDF? Okay. So can I say? So see, the thing is here for the case of discrete, we directly connected this using this probability x less equal to x. Here we said it for the case of continuous. We said this, but we do not know actually what the random variable is. Then the question will be somehow, can this kind of a probability, this kind of probability of certain events can be found using the cumulative distribution function? And yes, it is possible. So we'll summarize all these results. Okay, as an idea, you can prove it. I'm not going to prove it. This is very simple. Okay, so let fx be the CDF. Okay, corresponding. You just use the definition. You'll see that this follows corresponding to a continuous random variable x. Then the following holds. One is p x this. It will be same as this. So now you may get a clue why I said before that if you consider a continuous random variable, for if you pick any instead of if you pick any x, then the probability of happening of this will be equal to 0. Here you'll see this, which is exactly the same as probability of x less equal to x. Because when you are integrating, I'm just giving a justification for this one, but for others you can also see this. So you are taking minus infinity to x, this one, and this one, minus infinity to x. They are not different when you perform the integration on this. Because when you are performing area, single value. So for example, here, suppose this is fx. Okay. So here you are computing its area, or let's say, yeah, you are computing the area. So whether at this particular point, this value is somewhere, okay, I make it different, so that will not contribute to the area of this one. This is obvious. So that's why this is always the case. So capital X is equal to small x, probability of that is same as probability of capital X less than x. So it is the same thing.
Excuse me, sir.
Yes?
So your screen is not visible.
For everybody?
Yeah,
So
for
your
us it is
For others? So you may just, yeah. Because I can watch, I can see it in my desktop, I can see it.
Sir,
So
due to
maybe,
internet issue for say 1 and 2 minutes, then I cannot see your screen.
no, but my screen is visible to others. So what you can do it, you can sign out and then again sign in.
Sir, I already do it.
You did it? Okay, but how can I help? What do you want me to do?
Can you share again?
Okay, I'll just stop sharing and maybe I'll share this again. Where is that stop sharing? How to stop sharing? How to do it? I forgot. Well, oh, here. Stop presenting. Now let me check. Yeah, in my computer also it is not showing. Now let me again share the screen. Now it is shared. Now you can tell me whether you can see it or not. I stopped the presentation and
yes, sir. Now is visible.
Okay. Oh, okay, great. Okay, so yeah, here. So this is 1 minus fx, and okay, this I am saying now I can prove it. Why? At every point it is 0 because x to x fx dx. What is its value? What is the value here? So for any particular point, what is the area under that curve? 0. So this is 0. So now we can prove it, which is completely in contrast with this random variable, discrete random variable, where there the probabilities are defined pointwise at the discrete values. But here, if the random variable is continuous, then probability for happening of a particular sample point is actually 0. So example I talked about, just you consider the the part of the wall you are in right now in your room. Let's say you throw a point or you throw your pen on the wall. And then if I pick a very tiny point inside that wall, inside that region of the, inside that part of the wall, okay, what is the probability that it will hit that tiny point? It's probability 0. And this is not for only single tiny point, it's for all possible tiny points. Okay, this is always 0. If you consider the entire part of this wall, okay, as your range set, as a sample space, okay, now then it is occurrence of this is exactly equal to 0. So that's why when you want to compute probability, okay, in the case of continuous random variable, then you have to consider at least some part of the region we talked about that it will hit in some area. Okay, you cannot talk about a tiny point. You have to talk about a part of the area of this, of your wall. Okay, so this is the difference between discrete and continuous. When you're talking about continuous, the happening of some particular event, you have to talk about a finite area. You cannot talk about a very tiny point inside that part. You have to talk about a finite area inside that part. This is the difference between discrete and continuous.
Sir?
Yes, yes.
Sir, then how can we define fx, sir?
fx we define using this, less equal to this, you see. And see here.
Small fx, sir.
Yeah, the capital F I am saying. And see here, I did not define fx actually. So this fx, the PDF, here this fx for the discrete, I defined this like p if x equal to x. But I did not define it this way. I said this f is defined using this, which is probability of this. So this f does not fx does not mean that it is a probability of capital X equal to small x. It is not for the case of continuous random variable. It is not. This small fx, it is not this probability of capital X equal to small x. It is not. This is the interesting part I'm saying. Although when you plot, it is defined pointwise. For each point, this is fx. But when you talk about probability, then you have to consider a part of this, not a single point. A single point does not represent a probability. But when you take a part of it, then the area under this represents probability. That's the difference. Because if you want to talk about area at a certain particular point, it is always 0. So you cannot talk about probability at a particular value. You only have to value in the range set. You always have to talk about probability at an interval in the range set. So when you take this, then this will give you area will consider you the probability. So this is the CDF. This is how I described. I did not say this is the probability curve, this fx, which was the probability curve when we talk about distribution. Let's say these points are representing probability, but here it is not the case. Here when you take the integration, so here it is defined. When we talk about the integration, yeah, this is how it is defined. So when we talk about the integration, then we say this x is in the set A. We did not say that A is a single point. If it is a single point, then it has to be 0. If it is an interval, then only it is non-negative. I mean positive. Okay, so you always have to talk about a finite area or finite part of the interval, not a tiny point, because this is also justified. If you know about quantum mechanics, because you have done physics 1 or physics 2, so quantum mechanics, this is the case, because you cannot never find a tiny point. How much do you increase the strength of your microscope? Okay, he cannot even define a tiny point. This is not possible physically. So it makes sense. I mean, even if you say, okay, let me find a point on the wall, you cannot find out a point on the wall because it is so tiny. And that makes sense in physical science, I mean in physics. That it makes a lot of sense. Yes, you cannot find, because you have to go to the quantum, subatomic level. It is so tiny that you can't even find it. Okay, so this makes sense actually. As in B, again, you can say that this is FB minus FA. If there is the same logic using the area, you can prove all this. Okay. Now I will introduce a new concept, which is called percentile. Okay. So now what we will do is we'll define different kind of measures. Okay, to talk about properties of this continuous random variable. because it is a little complicated. So in fact, we'll do it also for discrete random variables. So we'll define different measures for both discrete and continuous random variable. But here, for the time being, we first introduce a measure about continuous random variable. Okay, so this is specific to continuous random variable, and this is the idea which is called percentile. Okay, so I'm defining it only for the discrete random continuous random variable. But if I want to talk about the discrete random variable, okay, we have to know something about something called the order statistics of sample points. Okay, which we did not discuss. Probably we'll do it towards the end of this course. So that then only we can talk about it. But for the time being, we'll only talk about percentiles. So this, you'll see why this is important. Percentiles for continuous random variable. Okay, random variable. So we want to get some idea about the continuous random variable, and this is one way to get an idea. Okay, how does a curve look like? Something like this. So here, let us start with the definition first. We'll talk about what it means. So let P be a number which is lying between 0 to 1, lying inside, or is a number between 0 and 1. Then we call it 100 times pth percentile. I'll come to that, what it means. Percentile, 100 pth percentile of the distribution. Distribution here means the PDF of the random variable of the distribution of a random variable X is any real number Q which satisfies this. Probability of X less equal to Q is less equal to P, and probability of X bigger than Q is less equal to 1 minus P. Okay, what it means, first of all. What does it measure? Now you see, this is an event. What is that event? That X will take values less equal to Q, and this is the event that X will take values which is bigger than Q. So if you have this kind of a thing, this is the real line. Okay, this is the real line, and Q here. Okay, this is the point Q. Then X will take some values here, which is less equal to Q. Okay, this event. Okay, and this event, X will take values bigger than Q. With this. Now, what I'm saying here is probability of this event that it will take the value less equal to Q is less than equal to Q. Okay, and this is less equal to 1 minus P. So that means what I'm trying to do here is I'm trying to divide this probability curve, not as probability curve, but the density function, let's say, into two parts. So this Q, so this is the Q, let's say, this value, and area of this is less equal to P, and area of this is less equal to 1 minus P. And if you consider this to be equal, it means happening of the fact that your event is here, or the sample point is here, that will occur with probability P. And this here, the sample point is here, is probability 1 minus P. And Q, it is this value Q, which is dividing that. Okay, but how to find this P, for example, given Q? You have to find this event and then you have to find this P. Or suppose you know the P. So this is with P, this is with 1 minus P. If you know P, then you want to find out Q. That how this particular Q divides the entire region under the curve Fx. So this basically what is happening, this 100 pth, this is a measure, 100 pth, okay? It is a measure, okay? It is kind of measure of a location Q, okay? Such that finding Q finding the location Q such that, so if you know the value P, then you have to just use this to calculate Q. Location Q such that, okay, Q divides the distribution, into two parts, or the distribution mass or the density into two parts. Okay, one with probability P, one with mass P, another with mass 1 minus P. Okay, let us solve a problem, then everything will be clear. Let's see example. Suppose, let's say the PDF of a random variable is this. Something, let's say to the power, this is the continuous, okay, random variable. So this for x less than 2 and 0 otherwise. So we have a function, okay, which you can plot. So then this is the thing. Then the question is, what is 75th percentile of x? What does it mean? I'll tell. That means 75th percentile means 100 times P is equal to 75, which means P is equal to 0.75. That means I am looking for, so if I plot this, function, let's say this is 2 and rest are 0, okay, less than 2. So it is some kind of this, let's say, okay. So I am looking for some point Q such that this curve, okay, let me draw it here. Let's say 2 is here, so this function is 0, function value, and let's say this is something here. So I'm looking for Q such that the probability of mass here is a 75% of the entire mass. So I'm looking for this value Q. That left of this, okay, the mass is 0.75. That means the 75% of the area under this curve is happening left of Q, and the right of Q is only 25%. Okay, and this will particularly play a big role when we talk about median. Okay, we'll come next, but let us solve this problem. So we find this P. Then what do we have to do? We have to use the definition to find Q. What is my definition? My definition is this. So that means I have to find Q such that, find then Q such that minus infinity to Q fx dx should be equal to P. So which means minus infinity to Q, fx means x minus 2, okay, dx should be is equal to 0.75. And if you do that, so it will be e to the power x minus 2 minus infinity to Q 0.75. So e to the power Q minus 2 is equal to 0.75. So it means Q is equal to 2 plus log of 3/4. So if you take this particular value of Q, then the left of Q will be the 75% region under this curve. That's why this will give me some idea about how it is distributed. Now, what is the portion? What is the particular point such that I want to find my area? I will find the mass value of this random variable, or the mass value of this distribution is left of this or the right of this. Okay? And in fact, if this, okay, so let me just define it. Okay, the 25th and 75th. So that means whenever the region here, suppose we have some region here, okay, then let's say this point, let's say Q1, okay, Q1. So that means here the region is 25%. Now let's say Q2, okay, then here the range, here the entire domain here under this entire this thing, this is 75% mass. left of Q. So the 25th and the 75th percentiles of any distribution are called the first and the third quartiles. They're called quartiles, Q-U-A-R-T-I-L-E, respectively. First and third quartiles, respectively. And specifically, you are interested to know what is the point. Okay, let's say this is my fx. What is the point where this area is divided into halves? Like half of this is in the left of this and half of this in the right of this, and this is the point Q. And this is the 50th percentile is called actually the median. So this is the point, the median of the distribution, where it divides the entire distribution into two parts. The curve under this is the 50%. This is the 50th percentile of a distribution is called the median of the distribution. Okay, and another thing is also very important. So regarding the continuous random variable, if you plot, suppose you know, so this is another idea. Suppose you know, and this is what happens in real life actually. So anyway, so suppose you have some kind of a PDF like this. Okay. Then at this particular point, you'll see that this is picking some value, this is picking some value, and this is picking some values. Okay. So locally, this point, okay, this is taking a maximum. So this is local maximum, which you have studied in calculus 1, or it's also called relative maximum. So at this point, so probability is very high around this point. You can see like this, because we cannot talk about probability at a point. We have to say probability nearby this is very high, okay, compared to these values. Okay, so relative maximum, and these points are called modes. So what is mode of a distribution? Mode is the point, okay, or the value of x where fx attains local maximum or relative maximum. So maximum. So how do you find modes of a function? For example, I ask you, what are the modes of, so it can have more than one mode of a particular distribution. What are the modes of the Cauchy random variable? So how to find a local maximum? So Cauchy random variable, it is 1 by pi times 1 plus x square. Let's say I'm taking Cauchy 0. In order to make my life simple, the theta value is 0. Okay, that means theta is equal to 0. So this is my random variable. This is a PDF of Cauchy random variable. How to find this?
Sir, if that is equal to 0.
Yes. So we have to take the derivative of this and make it equal to 0. Whatever the values we'll get, they are the local maximum, the relative maximum. So here I'll get fx. That's the derivative of this, which is derivative ddx of f, which will be minus 2x by pi 1 plus x square whole square, and I'll make this to be equal to 0. Okay, and this means x equal to 0. So x equal to 0 is the mode. So now we even did not plot the Cauchy distribution, but we have some idea now that there is a bump at 0. If we draw the Cauchy distribution, we'll see that there is a bump at 0. So there are complicated function, complicated distribution, or some distribution. Even if we do not plot it, but we can say something about this distribution. If we calculate, let's say, percentiles, the 100th percentiles, or modes, or the medians, and we have some idea about those PDFs. So that's why these things are important. Okay, the mode, the median, or in general the 100th, they are the measures. Okay, to understand how does the curve look like, even if you don't plot the curve, even if the function is very complicated, but you manage to compute the derivative. Okay, or you manage to compute the integration. From the integration you can compute the percentiles. Okay, the median, or let's say the 25th percentile or 75th percentile. Okay, and then accordingly you will get some idea about the PDF, even if you did not plot it. Okay, so this is nice. Now we'll introduce some more. I can take a break here, but it's just 14 minutes left, so there is no point in taking a break. So we now talk about some general measures for both continuous and random, continuous and discrete random variable. Okay, so first of all, I will talk about what are called moments, okay, of a random variable. So this is for both discrete and continuous. So moments. So these are also measures, okay, which can give you some idea about the random variable and hence some idea about the probabilities of the events associated with the random variables. So moments of random variables. Here, random variables it could be both discrete and continuous. So we'll see random variables. What does it mean? We'll see. And we'll see what is called the expected value, expectation, and the variance. Okay, and gradually we'll talk about Chebyshev's inequality. Okay, let us define this. Okay, definition. We'll see. Let us first define it. The nth moment, or nth order moment, some people will say. Nth order moment. I'm not writing order. So nth moment about origin. It could be about any point, but about origin. This is in the syllabus. Oh, we'll talk about it when we talk about at any other point about origin, or sometimes it's called central moment. Okay, in some books they'll say central moment. Moment about the origin of a random variable x. Okay, and let us denote as this, denoted by e, okay, of x to the power n. In some books you'll find this parenthesis as third bracket. Okay, this bracket is a third bracket, but we'll use the first bracket. This as this. So this is a value associated with x to the power n. Okay, I'm telling what is x to the power n and how it is defined. For discrete case, it is defined as this: small x to the power n fx. So if you know the PMF, and this x is in the range, so x is a real number, so it makes sense. Now see, you'll see everything we'll be discussing in terms of this range set of the random variable, because they are the real numbers. We can talk about addition, product, and so on. So this is x to the power n times fx for each x. So if x is discrete, and we'll say integration minus infinity to infinity. Because here does total Rx, here the total is minus infinity, x to the power n fx dx if x is continuous. So if n equal to 1, then you have e of x to the power 1. We will just add e of x. It is called the first order moment, or the first moment. E n equal to 2, we have x square, okay, which is the second moment. The second moment, and these are all about the origin. Okay, about the second moment, and so on. The third moment, the nth moment, basically. Second, but these two are I'm specifying because this will be using later on. These two are very fundamental. The second moment.
Sir, what is the significance of the moment?
Yeah, I'll talk about that. Don't worry, I'll talk about it. So I'm just here, I'm just associating, I'm just defining some number. Okay. I'm just defining some number. We'll talk about that, what it means. Okay. So first of all, our question should be whenever we are defining something in mathematics, some formula. So this is kind of a formula. You give me some random variable, suppose for the case of discrete, I know this value is small x, I know the PMF, then I can compute this value. Possibly. Here also I know some x. Okay. I mean, I can compute this. If I know this fx, I can compute this integration. I will get a value. I'll call this as the nth order moment. But first of all, is it always be computable? Meaning, does this always give me a finite number? That's the first question. Okay. Is it always finite? Okay. I'll show that this need not be finite. That means moments need not be finite numbers. And in those cases, these are useless. Okay. So here, if this x is infinite, countable infinite, then this is a series. So I will talk about whether the series converges or not. And when, for the case of continuous, I have to talk about whether this entire function is integrable or not. So anyway, so here just a point, just a note, let's say, moments may or may not, okay, exist. Okay, that's the first thing. Now, when n is equal to 1, like this is, it has a beautiful name. In fact, it is called the mean or the expectation. And it has a notation as well. Okay, so I'll come to that first. And yeah. So first of all, let me say, okay, let me use the definition. The mean, which is denoted as mu in most of the text, but I'll denote the mu x because it corresponds to a random variable, mu x. Okay, the mean mu x of the random variable, okay, x, capital X is defined as this mu x, which is, so this is the expected value, or you can say mean, x fx, x belongs to the range set. If x is discrete, and it is minus into infinity, x fx dx, if x is continuous. Now, if I want to give a meaning to this number, what it possibly be? Okay, for the time being, let us forget about the continuous part because it is a little complicated. I have to talk about it in terms of area and the product of this and so on. But here it is quite meaningful. Why? Because this is nothing but sum over x fx, next is in the range set. It is nothing but sum over x p of x equal to x, because that's how the PMF is defined for the case of discrete random variable. I already explained this. Now assume for the time being that I have a random variable, but these are the possibilities. Let's say x1, x2, and so on. Okay, and they are all equally probable. Okay, that means this is just the average value of the corresponding. So this p of x, let's say all are equal. So say it is finite and the number of points in the sample space, or these are the number of points in the range set is, like say some k, then these values are all 1 by k, and then it is just the x1 plus x2 plus dot dot xk by k. It is just the average value of this. Otherwise, how we can explain it? Let's say assume for the time being, this is just for the past purpose explanation. Okay, explanation, which is, let's say the range space of x is nothing but, let's say, x1, x2, some xk. Then mu x is nothing but x1 p of x equal to x1 plus x2 P of x equal to x2 plus dot 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 plus xk, P of x equal to xk. Now, what are these probabilities? These are like you are dividing the entire number 1 into some parts. It's a proportion of the, if you consider that 1, that the entire probability 1 as 100%, then this will talk about percent, some percent, this will give me some percent, this will give me some percent. That means in the total, this means it is kind of an weighted average, or the weights are the proportion corresponding to the probabilities. So how much amount of x1 you will take? It is coming with some value weight. This probability of capital X equal to small x1. How much amount of x2 you will take? It is coming with this. So it is the probability of occurrence of x1 times the value x1 itself. Here is the probability of occurrence of x2 times the value x2 itself. For example, x1, x2 could be like head and tail. Okay, and head can be assigned, let's say x1, some value, let's say 1, tail could be 2. Now, if the probability half and half, so let's say h corresponds to 1 and tail corresponds to 2. I want to find out the mean. So if they are occurring, if the coin is biased, unbiased, then it is occurring with probability half. Otherwise, I'll have some probability p1 for the head and 2 times probability 2. So how much portion of 2 can be, how much portion of 1 can be. So it is kind of an average weight. It is not, it's a weighted average, or so let's say it is weighted average. So the meaning of min, okay, min is, it's not exactly the average. Average means the central value. Okay, average of some number is like the central value. But mean means it's weighted average, so it is a tendency of the central value. Okay, is measuring the measure for central tendency. What does it mean? So this is meaning, which means, okay, this is a value, the random variable takes. If I know this value, that means suppose this value is 5, then I will assume that the random variable will take the value close to 5. Here, if you compute, let's say it is half, or probability something, let's say 3 by 4, it is probability is 1 by 4. If you take, you'll get some value. So 1 by 4 plus 6 by 4. If you do that, 4, this is 7. So this value is 1 point something, right? 1.2 or 3. This will be 1.5, right? No, not 5, 2 point something, 1.25 or something. Anyway, 1.2, let's say. So if I know this, that means the values are close to 1.2. Now here you see this is 1 and this is 2. Right? So it is a central tendency. What is the central value here? Central will be half times 1, that means half plus 2 into half. So this is 1. So 1 plus 5. So 1 plus 5 was the central value, like the average. And I'm getting here is 1.2. It is close to the center. So it's a measuring tendency of the central value. The value of the random variable, what I was saying here is the random variable takes or assumes on average. On average here meaning in sense of weight, okay? On average means in sense of weight, but yeah, we can say average inside this. So that's why it is also called the expected value, which you can expect for the random variable. Your random variable is considering some values, x1, x2, x3, dot, dot, dot. So if I give you like, what is the possible value of x for any sample point? It is this value, which is the expected value. It is nearby to that expected value, okay, of the random variable. So it is called the expected value of the random variable and denoted as x, which is the mean. Okay, I have to stop it here. We are running out of time. Tomorrow again, we'll define some measures, okay, and try to complete it by tomorrow the syllabus. Yeah, if you have any questions, you may please ask now.